Last week we were doing waves. This week we're doing waves, but a particular kind of wave, an electromagnetic wave, a light wave. You get a rope wave when you take a piece of rope that's sitting there and it's stretched, and then you shake it, and then a wave travels. You get a sound wave when you take some air that's sitting here, and you shake it, and the sound travels. This is the way waves are made. Suppose you had a piece of electric field. Let's say you have an electron, and that electron has an electric field coming out of it, or if it's moving, it has a magnetic field coming out of it, and now you shake that. That is how you make an electromagnetic wave. Whether it is radar, whether it is a light wave, whether it is ultraviolet, whether it's an X-ray. These are all kinds of we call them electromagnetic waves because when you're moving the electron, it has a magnetic field too. So you're shaking the magnetic field, you're shaking the electric field. They each carry about the same amount of energy, and this wave goes off. And an electromagnetic wave is one of the key things in all of physics. And as I said, it's light, it's microwaves, it's radar, it's X-rays and gamma rays. These are all electromagnetic waves. The only difference between those different waves turns out to be the frequency, how fast you shake it. If you shake an electron up and down 6 times 10 to the 14 cycles per second, that's faster than I can do with my hand, then the wave that comes out has a frequency of 6 times 10 to the 14th cycles per second. And we call that visible light. We call it visible light because the human eye has detectors in the back of it that can pick up that frequency. It doesn't pick up other frequencies. The other frequencies I like to refer to as invisible light, just to stress to the fact that they are very similar to light. It's just that your eye doesn't sense them. If the frequency is a little bit lower than what your eye senses, it's called infrared. That's because red is the lowest frequency your eye can sense. If you go beyond that, it's infrared. It's there. It's like light. You can form images on it. In fact, cameras can see it because the sensors on the camera are sensitive to some frequencies that our eyes are not sensitive to. So sometimes you'll see a film. You tend to see these more in horror movies and when there's a war going on. And the reason is infrared detectors are used. I have one in my camera, actually, and I use it to photograph my daughter when she was dancing in a very dimly lit hall. And you have this camera here, and you can barely see her, and you turn this thing on, there's a bright image in it. Now, what's happening is we have a light bulb in it that's emitting this infrared radiation, and the infrared radiation bounces off her, because that's how you see things, goes into my eyes don't see a thing. But it goes into the camera sensor actually detects the infrared, so I get a little image in the camera, and then when I put it on a TV screen, it's invisible light, so I can see it. So this is what light is, and you get light by shaking electrons. That's the fundamental way you make light. Now, if you heat something up, it glows. We'll be talking more about this next week. Why does it glow? The reason is you're heating it up, and so the atoms are shaking. The electrons are shaking too. The electrons are shaking a lot more because they are so light. Very light particles, you remember, keep the same energy as the heavy particles, but because they're light, to have the same energy, they have to be going faster. So when you heat something up, the atoms shake, the electrons shake faster. Shaking electrons make light. That's why when you heat something up, it glows. That's how ordinary incandescent light bulbs work, the kind where you heat up a filament. You have a little wire of tungsten. You send electricity through it. Because of the resistance, the electrons traveling through heat up the atoms. The atoms heat up the electrons. The electrons shake even at higher velocities, and so they emit light. And that's what we see with an incandescent bulb. So this is what light is, and light is a wave. By the way, the inventor of physics, there were several people who invented physics, but there was one guy who really invented it. I mean, Galileo worked out a few things, and Kepler worked out a few things, but then along came Isaac Newton back a long time ago, and he worked out most of what we call physics these days, except for the modern physics, which came in the last century. He worked out a lot of the basic physics, but he got light wrong. Very tricky to figure out what light is. He never knew light was a wave. The reason is the wave packets are so small that in ordinary life you don't experience them. You know, a wave can be continuous, going on forever, or it can be it could be little packets. And when the packets are so tiny, the wavelength of visible light, I said the frequency was 6 times 10 to the 14th cycles per second for visible light. That's a typical number. So you don't have to know it. A cycle per second gets a name because, hey, we got to honor somebody. Why waste it on just a name like cycles per second? There's no famous scientist named Dr. Cycles. So let's call it a Hertz, named after Mr. Hertz, who actually invented the first radio communications. So this is visible light. Now, you may remember a couple of other facts. Last week we had an equation that said that the velocity of the wave was equal to the frequency times the wavelength. We worked that out. It's simply because if you're going 1,000,000 times per second, in 1/1,000,000th of a second, the light travels one wavelength. That gives you the velocity. Velocity is one wavelength per 1,000,000th of a second. So that's that equation. Now, the velocity of light, sometimes we call the velocity of light, we give it a symbol c. C is not always the velocity of light. C is the velocity of light in a vacuum. And that's the number that I told you is about 1 foot per computer cycle. Some of you have faster computers these days. I just got my 2 gigahertz computer. But if you think of a computer as typically 1 gigahertz, 1 billion cycles per second, how far does light go in 1/100000th of a second? The answer is 1 foot. So light travels really fast because 1/100000th of a second is so short. On the other hand, your computers do a whole thing in 1/100000th of a second. That's why they have to be small. Because they'll be doing a calculation, they'll go over here to get something from memory. The signal can't travel any faster than the speed of light, as we'll see when we get to relativity. And so if it wants to get information back and forth, it doesn't get it fast enough. It's sort of like if you want to call someone up and there's a 10-second delay in what you say to them. It's only so much you can do. So the speed of light is a major limitation for computers. That's one place where the movie 2001 really got it wrong. They had their computer being huge. HAL was this huge, big thing. Computers have to be small because they operate so fast. That's a key part of it. So this is the velocity of light. And it's about 1 foot per computer cycle. I could write that another way. This is about 3 times 10 to the 8th meters per second. And now I could use this equation. I have the velocity, I have the frequency, and I can get what the wavelength is. And the wavelength turns out to be about 0.5 times 10 to the minus 6 meters, or what we call a half a micron. And I do want you to know that. I want you to know a micron is the smallest. Actually, this is about the smallest thing you can see in a microscope. And the reason it's the smallest thing you can see in a microscope is because it's the size of the packet of light. And trying to see something smaller than the actual packet of light, the packet of light will bounce off it, but it won't show any detail. So the smallest thing you can see in a microscope is about a half a micron. Red blood cells are typically 5 microns in size. And so those of you who worked in medical business looking at red blood cells know you see this thing, but it's kind of blurry. Because you see, here's this red blood cell, and it may be 5 microns in size. And if you try to look at it, you can see only it's like 10 pixels going across it. Because the smallest part you can see is a half a micron. And most microscopes don't even get to that limit. Typically, the microscope will get down to 1 or 2 microns if it's a really advanced microscope. So you're not going to see very many different parts of the red blood cell. So the whole thing will look fuzzy. This has happened to me, but when you work with microscopes, I used to work with microscopes a lot when I was younger. And you look at these fuzzy things and you wind up thinking the objects are fuzzy. But it's not. It's because you can't see it any better because you're at the wavelength of light. And then along come a better way of photographing it, something using a shorter wavelength. Typically it's done these days with X-rays, or actually, we'll talk more about this when we get to quantum mechanics, electrons. Electrons also have a wavelength because they are also waves. If you use those to make an image, they bounce off things just like light does. And then you see a red blood cell, and instead of a red blood cell looking like this, like this, you see the red blood cell looking like this, with all sorts of little things in it. You know, all this little detail. You know, you say, hey, it's really there. Not a fuzzy thing, but this is the limitation of light. Because the packet is so small, Newton thought light was a particle. And he treated it like that. I mentioned this is the speed of light. In the vacuum, when people say they're slowing down light, gee, I could slow down light. It's rather easy to do. Let me do it. Watch. It's not a very good demo. Here's a piece of glass. And what happened to my little light emitter here? My pockets get so full of junk. Here it is. My little light emitter. Okay, little light emitter. It goes through glass. I've slowed down light. Actually, I've slowed it down quite a bit. When light travels through glass, it slows down by a factor of 1.5. That's quite a lot. It really slows down. Why does it slow down? Well, remember, light is a wave of electricity. When that electricity enters the glass, we have the electricity in the glass. It's an electric field in the glass. That electric field in the glass starts making the electrons move up and down, the glass electrons. In a vacuum, there's nothing for them to move up and down, but when they get into the glass, so it's as if the electromagnetic wave suddenly has this extra mass on it. It has these electrons that move with it, and that's what slows it down. Light going through air slows down. Only it's less than 1%, about a part in 1,000. But it does slow down compared to the vacuum, and that means light can bend, because you know when waves go, and if you're going through, if you have something here where light goes slow, like glass or water, and the wave is going this way, it will tend to bend towards the slower side. And that's how we bend light. That's what lenses do. When light goes through a lens, it changes its direction. It does it by making use of the fact that light travels slower through it. Now, I list some of the sort of applications here that are all based on this. Light is such a high technology that we may not be at the peak of light technology just yet. When you use the internet, when you're connecting to, I don't know, Romania or China on the internet, most of the information that's flowing between you and China is flowing through light beams. How can that be? Well, it makes a lot of sense, because light is just a wave, right? And the way that you make a radio signal is you send an electromagnetic wave, and if you want to send Morse code, you turn it on and off and on and off, and you hear the signal come in, then it'll stop, and then it'll come in, stop, long, short. You can send the code like that, or you can send a sound. You can send the sound information. To send sound information, what you do on a radio you have this electric wave that's going really fast. Let me do it over here. Aha, the secret back room. Sound waves might be 1,000 cycles per second. And you'd like to send over a radio my voice at 1,000. 1,000 would be more like this. That's more like 1,000. Radio waves are typically thousands to millions of cycles per second. Let's say here's a radio wave. So this is what they do. They'll send a radio wave that looks like this. And this will represent this. And what the radio receiver will do is take this wave and measure, take this part of it, and that's made to be a duplicate of this. That's called modulating the radio wave. That's how radio works. This very high frequency wave. Why do we use very high frequency radio waves? Well, because they travel far. Because you can go from here to San Francisco or from with a radio wave. They travel very well through the atmosphere. So by changing the radio wave, it's called modulating it, then when it goes into your radio receiver, it smooths this out and then puts the resulting signal into the speaker. The speaker goes and vibrates the air, and you hear the voice. That's the way radio works. There is a fundamental limit to the amount of information that you can send with something like this. Suppose this is called the carrier. And typically for a TV, we're talking about millions of cycles per second. So it's millions of hertz. Suppose, here with these millions of hertz, we're trying to send a signal that is even faster than this vibration. Suppose the signal we'd like to send is a billion cycle per second computer signal. Okay? Then a million cycle per second signal, if you try to send then the signal you're trying to send doesn't go up and down slowly, but goes up and down faster than this signal. So you wind up canceling it out. This is getting kind of abstract, but let me come down to the bottom line. You cannot send a signal faster than your carrier frequency. So if you have a million cycle per second radio wave, you can't send more than 1,000,000 bits per second over it. This is very fundamental to modern technology, and it's going to explain a lot of the things you see in the world today. So here it is. I listed up there as the Shannon theorem, B equals F. What I mean by B is the number of bits per second that you can send is always less than the frequency of the carrier. Let me just say this again. If you have a wave that you're sending and you would like to send a signal with it by turning it on and off, you can't turn it on and off faster than once per cycle. If you do, you're actually sending a higher frequency wave, and that may not go through the atmosphere. So if you have a wave that has a certain frequency, the most number of bits per second you can send is the frequency. This was such a major discovery in 1945 that it has affected everything. The man who did this, Shannon, in 1945, this is called Shannon's theorem. It's usually stated a little bit more complicated way. It says that the band pass is equal to, no, the information content is equal to the band pass times the log to base 2 of the signal to noise ratio. But basically it's this, okay? The bits per second you can send is limited by the frequency. You can always send fewer bits than that. Now the reason this is so important, it really explains a lot of communications. For example, your AM radio, how much does that have to send per second? Well, typical music is 1,000 cycles per second. So you need a radio wave that's much faster than that, maybe 100,000 cycles per second. A typical radio wave may be 100,000 cycles per second. And then you can send music over that. That works just fine. Try to send TV over that, it will not work. Why not? Well, in a picture of a television, typically you have a whole television screen. There may be, I don't know, 640 lines. Let's simplify it. Let's say it's about 500 lines this way and 500 lines this way. 500 times 500 is 250,000. You have to send 250,000 individual picture elements every second, every 30th of a second, because the picture is updated every 30th of a second. Actually, it's every 60th of a second if you consider all the pixels. And so you can't send a signal like that with a low-frequency radio wave. Not if you're going to update it 60 times a second. There are too many bits. So you need a higher frequency wave, which is why television uses microwaves. Television has higher frequency than radio. Suppose you really want to send information. Then what you need is something very high frequency. Where do you get something really super high frequency? Light. 6 times 10 to the 14th. With a light beam, you can turn it on and turn it off 10 to the 14th times per second. A billion is 10 to the 9th. This is 100,000 billion bits per second can be sent over a light beam. You just have to turn it on and off. This is the modern technology of communication. It's done with light. Light is sent through things called fiber optics. I could take plastic and bend it like this, and I could send light inside of it. And the light, see here, this is not good fiber optics because some of it's leaking out the edges. And that's why you see it, which is why it's a good demo. But with really good fiber optics, it doesn't get out. It stays inside. We'll talk about, the way you stay it inside is you actually make something that's exactly analogous to the sound channel. Modern fiber optics has inside of it a variation of index of refraction. Index of refraction refers to the speed at which the light travels. So in the center of the tube, along this light channel, the very center is made out of a glass or plastic where the light travels slowly. Here it travels fast. Here it travels fast. So you put light into it, and it tends to go like this. And it stays in the center. It doesn't get out. It really is just like the sound channel. And this was one of the major developments. The original fiber optics were just tubes like this. And the light would bounce off the inner surface. And a lot would get out, especially if the surface were not perfectly smooth. And now this is a high-tech industry making these fibers. You can make them tens of kilometers long. And the light will travel a long, long way. And then what you do is you send bits by blinking it on and off. And this is the modern communications. And when you use the internet, you may use a radio wave to get from your computer to a radio station, to the internet. But then the internet will change your signal from a radio signal being turned on and off to represent bits to a light signal being sent on and off. And it can send these from thousands of different people all simultaneously. I mean, the easiest way to do it is to take your signal and send your signal. It can make it so fast that if it sees you've sent 30 bits, it can send those 30 bits much, much faster because it's doing it really by modulating light, and light is a high frequency. You can send that signal in a billionth of a second. So it can send your signal in 1 billionth of a second, someone else's signal in the next billionth, as long as it keeps track. Typically, it sends these things in what are called packets. So your computer will take a sound or a picture or something, break it up into packets of bits. That packet of bit will be sent over the radio relatively slowly. When it gets to the internet, that packet is then turned into a very fast packet. Instead of it taking thousandths of a second, it takes billionths of a second. That packet then can be moved in with other packets and sent over the fiber optics, because the fiber optics has such a high frequency carrier that the signal can go very quickly. Some people believe that in the future, instead of sending electronic signals, you know, we use wires in our computers. And we send electrical signals. I said last week, electricity is sort of the high-tech technology of the modern era. Well, there are some people who have a vision that will look back on this with nostalgia. Well, we used to send signals using electrons. Ha, ha, ha. Remember those? Come here, child. Let your granddaddy tell you the story about how we used to have computers that used electricity. Ha, 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 ha. Yeah, electricity. You haven't heard of that. Well, let me tell you about it. You know, so here's the future prognosis for you. So what will they use instead of electricity? There are some people, I'm not really completely convinced by this one, who says what we're going to be using is light. That you'll have light traveling around inside little fiber optics. And then we know you can make computers like this. You can switch light on and off. You make computer switches. Some of the largest industry in the world today has to do with the internet and maintaining this huge network of light. Because information is being spread all around the world these days on the internet, which is largely fiber optics. This is why your telephone calls, by the way, are also fiber optic. People used to think, go back 20 years and say, how will communications work in the future? Oh, the new high technology is going to be microwaves. And in fact, there are these microwave towers. These are things that emit things at typically hundreds of megahertz. Hundreds of megahertz for a microwave, maybe even a gigahertz. Okay, so let's say a gigahertz is the carrier. A microwave is a light wave with a frequency of about 1 gigahertz, sometimes higher. It can get up to 30 gigahertz. Billion cycles per second. So there are microwave towers. And microwave towers will take the signal. Usually they don't put them in packets because that's a relatively new technology, but they will modulate the signal to carry not quite 1 billion bits per second. And this was going to be the future. And I still remember making phone calls. When I was in Europe, I would call my children. And we would do a little experiment. Because, you see, my signal then was being sent to a local station that would then beam the microwave up to a satellite. And then the signal would come back from the satellite back down to the ground. And we could hear the time delay. Because it took such a long trip up to a geosynchronous satellite and back. It's just a fraction of a second, but it was enough that you could notice it. But these days, that technology, 20 years ago, people might have said that was the coming technology. I might have said that was the coming technology. This is why I limit myself to 20 years. Here we are now in the future, and we don't communicate to microwaves, to satellites. Why? Because microwaves have too low a frequency. It's only, 30 billion cycles per second. Instead, we communicate using visible light at 100,000 billion cycles per second. Well, how do you communicate from light from here to there? You put in a fiber optic, a piece of plastic that carries the light through the equivalent of a sound channel so it doesn't hit the edges and doesn't get lost and can go hundreds of kilometers. Now, you go 100 kilometers and the light is getting weaker. It is absorbed in the plastic a little bit. So they have a little detector that detects the light and then puts out a new beam. So it's an amplifier that's put online so that these things can go around the world. And this is how the internet works. The backbone of the internet is all fiber optics. The telephone company has been switching over to fiber optics. I don't know. I mean, they've talked for years about bringing fiber optics into my home. You think high-speed internet is a DSL line? When you get fiber optics there, you will be astonished when fiber optics comes into your home. Right now, you're using microwaves. You can do that. You can use microwaves because you're just one computer. And, having a signal coming in at 1 billion, well, you don't quite get 1 billion. With your microwaves, you're lucky if you get 1 million bits per second. Even less than that. That's partly because you're sharing microwaves with other people. So this is the communications. Now, that has to do with the frequency of light. And the frequency is so high that it becomes the preferred method of communications. There are higher frequency kinds of light. They're called X-rays, gamma rays. We probably will never use those for communications because even though they're higher frequency, there's a limitation that comes in from quantum mechanics. We're going to be talking a lot more about this when we get to quantum mechanics. Even with digital cameras, there's a fundamental limit that comes from quantum mechanics. It comes to do with the fact that light, even though it comes in bundles, if you have a certain frequency, the light is always absorbed in bundles called photons. And this becomes a major source of noise for current-day digital cameras. We'll talk more about that when we get to quantum mechanics. Now let me talk about light traveling in straight lines, which it more or less does, except, of course, it's not traveling in a straight line because the temperature of the air isn't exactly the same. And so the density isn't quite the same. So it may be a little bit warmer as you get up high, and because it's warmer up high, when the wave comes, it'll bend up a little bit, but you don't see that very much. You do see that in something we call a mirage. So in a mirage, this is how a mirage works. Typically, you'll have a hot ground. So here you are, and you are looking at the ground. Now, what does it mean you're looking at the ground? What it means is your eyes are accepting light that comes from the ground. When you're looking at the ground, you're saying, what kind of light is coming from that? We'll be talking about the eye in just a moment. So what kind of light is coming from that region? Now, light from the sky, I want to exaggerate it a little bit. When the ground is hot, and the air is cool, then the air above the ground also gets hot. This happens when the sun is shining really brightly on the ground. This kind of air will get hotter than that, and it could be a big effect. The light from the sky at that point is traveling, but not in a straight line, because the top part will go slower and the bottom part will go faster, and so it'll curve and it'll go like this. And so you see light coming from this direction, which you say, that's the ground. The light's coming from that direction, that's where the ground is, and the light is blue. You see blue light coming from that direction, you say, ooh, a puddle of water. Okay? But it's not. What's happening is the light is bending and coming up from the ground. It's sky light coming up from the ground. This is what's called a mirage. What your eye does is it looks at the direction the light is coming from, and now let me turn on this light on here. Can you see that over there? Now, you may have to move up a little on the corners. Can you see it over there okay? Just barely. If you move up a little bit, you don't want to miss this one. So I suggest that if you're really on the corners, you move back until you can see the light. See it right here. Okay? Yeah. You want to see this. You do. So move. It's good for your health, too. It gets your blood moving in the morning. I know that's something that all of you enjoy. Okay, now, this light here is one, gets a little bit hot. Whew. Okay, it's on for a while. I'm going to, this is not, I'm always sacrificing my flesh to good demos. And this is another one. I have to turn it, unscrew it. Take it out. Okay, there it is. Okay. What is that? I have a light in my brain? There's nothing here. What is it? Ah. I bet it's a reflection of this. Okay, that's what it was. There's nothing here at all. It's a reflection of that. And you didn't see this because someone left this box here by mistake. Okay, but it certainly seemed real, doesn't it? And it's a wonderful, this was, the first real large-scale use of this was actually in the theater. It was in the late 1800s. And it depended on a good piece of glass. In the original theater, they had you up like you were there. And then down here, what they had was, well, I mean, look, I haven't seen the play. I've read about it. But it was something like this. I wonder what happened to Marjorie when she died. I would sure love to talk to her ghost. But Marjorie, you're not real. Okay. Now Marjorie would be over here, the light shining on her. The audience would see this ghost. How many of you have been to the haunted house in Disneyland? The rest of you? You should go sometime soon. You should tell everybody it's not a requirement, but it's highly advised. If your parents are still paying for you, then you can tell them that this is one of those optional things that puts you at a disadvantage because most of your classmates have gone to see this exhibit that you haven't seen. And if you have been there, you can use the same logic to go there again. The haunted house has one of the most wonderful exhibits you will ever see. Running out of word space here. And it works as follows. What happens is you're on this little cart and you're traveling along, and you look down, and there's this dining table. Okay, big deal, dining table. And all of a sudden, ghosts appear, and they're swirling all around it. You know, you're seeing this. And then they disappear. Now, what's happening, of course, is the ghosts are actually not light bulbs, but they are pieces of silk and cloth that are moving around on a conveyor belt, and they shine a light on them. And when they shine a light on them, you see it, and then they're gone. And then they shine a light on again. Oh, they're back. You are seeing them just as you do here. Okay, you're seeing an image of it. And the ghosts can be made to come and go, and there can be real things here as well as the image. Okay? So the way this works in Disneyland is the geometry you'll notice next time you're there, if you haven't noticed it already. I keep on losing my chalk. They don't like me to lose the... Okay, is it works like this. Here you are, sitting in your little thing, looking. You are actually looking down on a region over here where there's a table set up. And you're looking at that. But in between you and it is a piece of glass. Most people don't notice the glass. They think, oh, it must be there to keep people from throwing things on the table, right? Or if they noticed it at all. You're looking through a piece of glass. Here underneath you, there are some ghosts being carried around on cables. There's also a little bit of a light that shines on the ghosts when they turn it on. When the light from there is turned on, then the light from this bounces like that, comes up to you, and you think the ghost is over here, just like it did over here. The illusions of Disneyland. They used to say that magic by magicians, well, you know, magic is making things like this disappear. Magic by magicians was done by smoke and mirrors. And there's a lot of truth to that, because the mirrors, until we got used to them, until we got used to high-quality mirrors, they were a major source of illusion. In fact, they still are an illusion. You hold a mirror up and you look at yourself and you take that for granted. This is one of the miracles of the modern era. Bible refers to through the glass darkly. You don't see yourself very well in reflections. These days we have very high-quality mirrors. By the way, I moved these here so that nobody would be able to look around the corner and see that there really was a turned-off light bulb right here. Okay. Now, this is making use of the fact that light bounces in the same way that it bounces off a that a ball would bounce off a wall. So just take a look at this for the moment. Suppose I have a face here, and you are looking up here. The light from the eye will get to you by bouncing this way. So your eye thinks it's coming from over here. The light from the mouth will get to you by bouncing this way. I mean, look, light from the mouth will also go this way. You just won't see that light. So I'm only drawing the light that gets to your eye. And that'll come by bouncing this way, and so your eye will think it's over here. So you get what we call an image of the face. And it's because light bounces like that. Now, if we curve the mirror, we can change all that. So let me try curving the mirror. You look in a mirror that's curved like this. And here's your eye looking, and here's the face. Okay, now, the light hitting your eye, because it's curved, the light that was going here would have bounced to there, but because it's curved, it'll bounce over more. So the light from the eye has to go higher to catch you here because of the curvature. So this is where the light from this eye will reach your eye. Light from down here, because it's tilted backward, actually has to get sort of way down here to come up like that. And as a result, your eye thinks, here's where the guy's eye is, and here's where the guy's mouth is, and it sees a big expanded image of the face because of the curved mirror. Because the light is bouncing right off the surface, but because it's tilted towards you, the light that reaches your eye is actually the light that comes up higher. And the light from here, because it's tilted backwards. So if you draw these diagrams, you begin to understand why these mirrors in the amusement park, when they're curved, make you look bigger or make you look smaller. Curvature of mirrors is the key to a telescope. And right now, what I'd like to talk about is how this imaging works. Because it's going to turn out that this imaging, the key to cameras, the key to your eye, key to spy satellites, all comes from a very simple principle. It's basically the same principle that these light packets go almost perfectly in straight lines. Now, it turns out they don't actually go perfectly in straight lines. The reason is they're really waves. And waves bend. And that's a pain in the neck. Because it turns out that that bending of the wave is the primary limitation on the ability of telescopes to see distant things, on the ability of spy satellites to read license plates on the ground. It's because these things really are little wave packets. They're not little particles. They're wave packets because they're waves. They bend. They bend when they go through holes. They spread out because they're waves. Spreading out isn't very much, but it's enough to limit the state-of-the-art things, typically a spy satellite. To see that kind of blurring, you have to be looking at things. You have to be looking at things that depend on really the small wavelength of light. Well, let me show you something here that is much simpler. A bunch of lights here. Okay, so there are 3 lights. Now I want you to remember there's 1 on the top and 2 on the bottom. Okay. This is not an illusion. This is now what I'm going to do is send this light through a hole. So let me pick a nice size hole. Here's a nice size hole. So there it is. Now the light's going through a hole. Now what's happening is we have these 3 lights, 1 on the top and 2 on the bottom. The light is going through a hole. The light on the top, light goes every which way. Well, let me make the hole a little bit more in the middle. Like that. But there's only one direction that the light comes through the hole, and that's this way. So here's the light from the upper bulb. The light from the lower bulbs comes up this way. So now let me demonstrate that. I'll need the lights off now, way, way down. So through this hole, the upper bulb, the light's coming down. Lower bulb's light's going up. You should be able to see that here. Okay, and you do. So what do you see? You see the light from the lower bulbs is coming upwards, and here they are. And the light from the upper bulb is coming down, and there it is. This is the basis. This is the basis of the human eye, of the human camera, of the spy satellite, of every imaging thing we have. This is what's called a pinhole camera. And there's the pinhole. And this may be the retina of the eye, or the film, or the digital detector on the back of your digital camera. And it's picking the fact that there's a light up above and 2 lights below. And so I take a picture, click, I record this. And then when I want to look at it, it's recorded, and there it is. But of course, I turn it over to look at it because I want to see it the way it really is. That's the way a camera works. But it's blurry. Why is it so blurry? That doesn't look much like a bulb. The reason it's blurry is this hole is so big. If you look at these light bulbs, they have a lot of little filaments in them. They have these glowing wires. Remember why they're glowing? Because the electricity goes through the wire. The electrons moving through the wire heat up the wire. The electrons move even faster because electrons are lighter. They're 2,000 times lighter than protons. They move really fast. They have electric fields. They put waves in the electric field, 10 to the 14th cycles per second. That's light. But we don't see that because this hole is so big. Suppose we put a really tiny hole there. Then we might actually see the difference between the top of the filament and the bottom of the filament. So let's do that because I can. And what I can do, The trouble is this cuts out light. But instead of this big hole, let me put a smaller hole. Here's one that's quite a bit smaller, about finger size. That'll cut out most of the light, but it means that the top of the filament and the bottom of the filament light will go to different places. So let's see if we can do that. Now we're really going to need the lights down. So you can turn them really off. And we can even, I want the lights down so much that I need to close the door. Okay, so there's light coming through this tiny little hole here, and let's see what we see. Okay, now you're beginning to see not just the fact that there's light there, but you're beginning to see the filaments a little. You can tell that these things are vertical, up and down. Let me try a really tiny hole. Not much light will come through, but if it's a really tiny hole, it can qualify as being a pinhole. And this one is really tiny. Not much light will come through. But let's see what we can see. So now you're beginning to see the filaments. That's actually, if you're up front, you can really see it right here. This is what's called a pinhole camera. And if you look up pinhole cameras, you have lights back, please. Look up pinhole cameras on the web. You'll find there are clubs that do pinhole photography. You get some film, and you take a box, and you put a little pinhole in the front of the film, and you put that box by the window, and you leave it there for 10 minutes, because there's not much light coming to that little pinhole, and then you develop the film, and you get a photo. And then you put the photo on the web, because you're so proud of being such a good pinhole photographer. Now, the key to modern photography is to replace that pinhole with a lens. By the way, your eye kind of works like a pinhole camera, except it has a lens. And so what your eye does is the light coming from above comes through the lens and comes to the bottom of your retina, where it's sensed and the signal is sent to your brain. And the light from below comes to the top of your retina. And the signal is sent to the brain. And some people ask the question, well, where does it get turned upside down? And actually, when you think about it, how does the brain know where it's coming from? How does the brain know it's coming from the bottom of the retina? Does the signal come along and say, hey, I was from the bottom of the retina when it gets to your brain? No, the brain has no idea what part of the retina it comes from. Little children, when they start looking at things, they're learning. So if light is coming from below, then the signal gets to your brain, and your brain doesn't know where it's from, but pretty soon you discover, oh, that's coming from down there. And if light's coming from above, your brain will learn it's from. How does your body do this? Here's a fascinating experiment that's been done in psychology class. I've never done it myself, but I'm really tempted. You can wear a pair of goggles that turns everything upside down. And they've done this. You wear it for a few days. Everything's upside down. And the first thing that happens is you reach for the light bulb. So here, let's say the light bulb is turned on. Whoops. Let's say I'm reaching for the light bulb. Okay? So my brain will see it, and I'll reach for the light bulb. Whoa. Whoa, wait, why is my hand down there? What's going on? Light bulb's up there, why is my hand down? Oh, wait a minute. Now my hand is up where the light bulb is. Huh, ugh, weird. That's the first day. I'm told that after a few days, you see the light bulb and you reach for it. Everything looks normal. You don't even realize things are upside down. Your brain has just relearned which part of the retina has signals from where. The weirdest thing, though, comes after you take the eyeglasses off, because then everything looks upside down, and your brain has to relearn it again. So, your brain learns, the brains are truly amazing things. Now, the way a lens works is it makes use of the fact that, let's see, what shall I erase? Here, let me just do this. That in glass, light travels slower. So, if you have something that's shaped like this, and light is traveling in this direction, the bottom part gets into the glass first. That's the slow part. So it bends towards the slow direction. Then it comes over here, and the top part gets into the air first. That's the fast direction. So the result is the light bends down like this. That's what happens when light goes through a curved lens like this. Here's a curved lens like that. It's thicker in the middle. Light from down here, the top part gets into the glass first, so it tends to bend that way. And then the bottom part gets out into the air first, so it tends to bend that way. And so it comes like this. If you put this out in the sunlight, what happens is the sun gets concentrated here, and you could start a fire with a lens. It takes all the light, makes it come to one point. Now, combine the lens with the big pinhole camera, and let's see what I can do. What I'm going to do is put this here, and I'm going to take this big pinhole camera. Let's see if I can make this work. I have to get a pretty strong lens. And let's see. I don't know if any of these lenses are strong enough. I didn't actually work this out beforehand. Let me try putting this in here and see what happens. Okay? Hey, that works pretty well. Not bad for an ad-libbed demo. What's happening? Why, with this big hole, am I getting such a good image? Well, here's the way it works. And this is the key to your eye, the key to satellites, to everything. Let me do that over here. There's a blank board. Oh, it's all the way in the back. That one, what happens here? Ha 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 ha. Whoops. Getting pretty close to understanding telescopes at this point. Okay, we had the pinhole camera. Suppose we have some bright spots. Here, this is a red one, this is a blue one, this is a green one. And here we have the film, or the retina, or the digital detector. The red spot, light comes through this hole there and there, so you get this big red blur. The blue light comes like this, bloomp, bloomp, and everywhere in between, so you get this big blue blur. The green light can go this way and can go this way, so here's the big green blur. So you get these three big blurs on top of each other with the big pinhole. If we make a small pinhole, and we have the red, blue, green, then over here on the film, the green light comes up here, and this is the only place it can reach. I get a little green circle. And the red light can only go this way. So we get only a little red circle. And here the blue light can only go that way. We get a little blue circle. But the problem is we've lost a lot of light because we have a small little pinhole. So the lens gets around that by doing the following. So for this, I need a third diagram. Let me take these down so you can see what I'm doing. So here's the third diagram. Well, maybe I'll just squeeze it right here. We have red, green, blue. We have a big opening, but now we put a lens in there. The light from the lens, some of the green goes up here, but it doesn't go up. It comes back like this. Some of the green goes this way. It doesn't go up. It comes back like this. And so we wind up getting a green spot here. If we put the film here, well, the light's spread out already. We get a big blur. But if you put the right film here, that's called being in focus. In a camera, what you do is you move the distance between the lens and the film until the film is right at the place where it's in focus. Then you get a little small spot. The red light, on the other hand, how does that go? Well, that bounces like this. The red light will wind up all focusing over here to a small spot. This is the green, and the blue will all focus over here. This can become a very complicated diagram. But the key thing is the light was spreading out. The lens makes it come back together to focus to a small spot. And that way you don't need a small hole. You can use a big hole. With a big hole, you can get lots of light. Camera lenses that have big lenses in front of them, they'll be listed like this. You'll see you have an f3.5 or an f1.4. These numbers indicate the relative size of the lens compared to how far it focuses. This is a very big lens. Actually, the small numbers are the big lens. So when you buy a camera, they'll say, oh, this is an f8. And you'll know that's a relatively small lens for its focal length. And it wastes, most of the light doesn't go through the lens. So when you're buying cameras, this is an important consideration. That's what a lens does. The lens of your eye does that. Now, the lens of your eye works in an interesting way. Here's a lens too. I can demonstrate this. Let me do this. So here I have light. I guess if the lights are down a little bit, that would be nice. And there it is parallel. And I can send that through a piece of plastic. And you can see how the light comes together. It's bent through the plastic, just like I was drawing on the blackboard. And it comes to a focus. I could also spread it out. If I do something that's backwards, I could spread the light out. Look at this. That spreads the light out. I could just bend the light into a different direction, like this. That's what's called a prism. Bends light in different directions. We'll get more to prisms in the next lecture. So this is the way lenses work. Now, I'm going to give you the simplest explanation of a telescope you'll ever hear, but it's going to be the most accurate. And even physics majors, if they don't get this explanation, never really understand telescopes. Okay. Suppose you want to look at the craters of the moon. What you can do, running out of board space here, but I think I can move on to this one. And just erase it. So this is the way telescopes really work. I'll first describe them in a way that's almost correct, but not quite, and then I'll make it really correct. So with a telescope, the moon is far away. That's the problem. If only you can get up close to it, you'd be able to see things. So let's do the following. Let's take a camera photograph of the moon, and here's the photograph. Now I can get as close as I want, right? Well, except I can't really focus that well because my eye isn't strong enough. If the thing is that close, I can't focus it. But if I put a lens in front of my eye, I'll be able to focus even on things that close. If you put a lens in front of your eye, you can focus things closer because the lens, the extra magnifier, these, where are my reading glasses? Here they are. These are extra lenses that help my eyes focus so they can focus on closer things. So I can focus now closer than I could without them because these add to the focusing of my eye. We'll be talking more about that in a moment. So here is the way a telescope works. Believe it or not, this is accurate. It is completely analogous to taking a photograph of an object and then looking at it close with a lens. Except you don't take the photograph. That's the only difference. That's actually less of a difference than you might think. So here's how it works. You take a nice big lens. Here's the moon. It's far away. You can't get up close. So here's a nice big lens. And what it does is it makes an image of the moon right here. So here's an image of the moon. An image of the moon is the thing where if you put the film there, you get the picture. It's the top of the moon is down at the bottom, and the bottom of the moon's up at the top, and here's the image. And if you put film there, you'd have the picture of it. And now you look up really close at the film, and you see the moon. But wait, we don't use the film. You don't have to use the film. Here you have a part where the light is coming from the top of the moon. All the light coming from the top of the moon is focusing on this port right here. And all the light from the bottom of the moon is focusing on this place right here. So this is a region of space that has light coming from it. Look at that, light's coming from this spot. Now what you can do is you can put your eye right here, put a lens in front so you can focus closely, and get as close to this as you want, and the fact that there's no film there doesn't matter. Because light is coming from that spot. And so you can look at that spot. That's called an image. It's a region in space where light is coming from it as if there were a little moon right there. There isn't a little moon right there, but it doesn't matter. Light's coming from that spot as if there were, and so if you look up close, it's like this. The light from the light bulb wasn't coming from here. It just looked like it was coming from there. This is also, well, you know, see, that's the thing over here is the image. Something where your light thinks it's coming from here. It can't tell the difference. Your eye can't tell the difference between there being a little moon right here and there being an image of the moon. It's the same to your eye. Light is coming from this spot. So now, here's this little image of the moon. But now you put it, I mean, a little image of the moon might be this big. Now you put your eye really close to it, and you put a magnifying glass there so you can focus, and you could explore all the craters of the moon. That's how a telescope works. That's how a microscope works. A microscope takes a tiny little object, and it has this special lens here, a very strong lens, that makes an image of this object, but it makes the image very large. So here's the creepy crawly. But it's an image of the creepy crawly. What happens is the light from the head of the creepy crawly goes through this and gets focused onto this spot. So here's the image of the head, and here's the image of the tail, and here's an image of all the legs. And there's this image up there. This thing is put very close to it, very strong lens, in order to make this as big an image as possible. So your red blood cell might have an image that's as big as this piece of chalk. So the light from the red blood cell is going through this lens and is sitting in space here. Now there's nothing really there except light passing through, but the light is coming from that object exactly as it would if there were an object there, just as this light is coming from this region exactly as it would if there really were a light bulb there. It's called an image. So now you have the little creepy crawly or the red blood cell or the bacterium or whatever is there, and there's this image right here, and you put a lens in front of your eye to help focus it so you can see it really big. And that's how a microscope works. What about a spy satellite? That's basically just a camera. A camera in space. And if you want a big magnification, what you need to do, I mean, this film here will give you green, blue, and red. Suppose I put the film further back. Then the green would be way up here. We'd say it's a bigger magnification. Green is way up there, and the red is way down here. And look how big this is compared to how big this is. So what you need to do to get a lot of magnification is you have the film way back from the lens. You may have noticed, for those of you who are into photography, if you have what's called a telephoto lens, a telephoto lens is one that sits way out in front of the camera. It does that so that the image has time to spread out by the time it hits the film and be bigger. Basically the way a telephoto lens works. It's they call it a long focal length lens. When you buy a lens, they'll tell you what is the focal length, usually in millimeters. A standard lens, ordinary photography, has what's called a 50 millimeter lens. So the film is 50 millimeters from the lens. If you want a telephoto shot, it may be 135 millimeters from the lens. In that case, the light has spread out more. You're getting a bigger image on the lens. I'm going to Africa in May, and I just got myself a 420 millimeter lens. So that will have really big images, which you need to do when the cheetah is really far away. So that's why you have the different focal length lenses. Your eye doesn't change. You can't change lenses on your eye. Actually, I did, but that's another story. Normally, you don't change lenses on your eye. And so what happens? Now, here's the problem with the eye. Here's the eye. And the eye has actually two lenses in it. There's something inside the eye, which we call the lens. Then there's out on the front of the eye, there's another curved surface called the cornea. And these are two lenses in a row. And actually, the cornea does most of the focusing. I want you to know that. There are really two lenses in the eye, the cornea and the lens. Here's the eye. Light from something far away, if everything is just right and your eye is relaxed, will focus to a single point on the retina, which has little cells to detect color and black and white. We'll talk more about that on Thursday. Color and black and white, they're actually, in fact, one of the things I want you to do before Thursday is go to a TV screen or a computer screen. I want you to look at white on that computer screen. And then I want you to look at it really close. Let's consider this a homework assignment for Thursday. You're going to look at it really close. You may need a magnifying glass to get really close. What I want you to see is there's no white there. What you're going to see are little red, green, and blue dots. No white, red, green, and blue. But as you back away, the red, green, and blue blur into each other, and that makes white. It's one of the most amazing illusions of the eye, is the fact that this happens. Okay, are we ready to give the quiz now? Just teasing the two guys who are leaving. They have a sporting event and they have to leave. So, okay, no quiz. Okay, now look what happens if the object is close. Suppose instead of looking at the moon, you're looking at a bug. It's up close. Now this light, when it comes through here, will bend also. When it comes through here, it'll bend. But see, it's already bent out. And so though it bends just as much, see, this light is going like this. This light will actually focus way back here because it's not parallel. The parallel stuff is bent just enough. If the stuff is moving out, then it's bent the same amount, but that's not enough to bring it to focus. So you have to focus your eye. Now, there are two ways you could do it. You could put in a more powerful lens. So here's a more powerful lens. Okay? So this will help me focus my eye, and I look at things that are really close. That's one way to do it. When you're young, you have another way to do it. What you could do is reshape this lens. There's a ring of muscle around that lens, and the lens is made out of flexible material. So when something is really close, what you do is you squeeze that muscle, and the lens gets fatter. It actually changes from this shape to this shape. And because it's fatter, it bends the light more, which is what you need when looking at something close. I want you to know this. That when you are young, this is what you do to focus things in close. You see something there, your eye is relaxed. You bend it a lot, and you can see things in close. Some of you are nearsighted. Nearsighted means this lens is already overly fat. Either that or your eye is overly long. Some combination of the two. As a result, you naturally focus at things that are close. In that case, to see things at a distance, you have to spread the light out a little bit more, like this. See that? This is the thing that spreads the light out. Can't see that too well with the lights on, but that's the light. That's one. So if you're nearsighted, you wear a little thing like this to spread the light out. Now here's what happens. This is an important thing for you to know. Will save you a lot of trauma, and you may be able to be very helpful to some middle-aged people by explaining this to them. As you get older, by the time you get to be an old man like me, what happens is the tissue here becomes less flexible. And so when you want to focus in close, your muscles squeeze, but that thing doesn't squeeze. And so you can't focus on things that are close, and you must wear glasses to see things in close. But if I want to see things far, I don't need the glasses. So when you're young, you want to see things far, you just look. You want to see things close, you just look. You squeeze the lens so it focuses. Then you look away and your eye has to relax to see things that are far. Get to a certain age and you can't do that anymore. Some people, what we say is we lose your accommodation. Accommodation is the squeezing of the lens. You lose your accommodation. Everybody loses their accommodation around age 35 or so. And then they have a trauma in their lives. Some of your parents may be undergoing this trauma right now. They say, my eyes are going bad. Actually, your eyes are going bad right now. If you try to see how close you can focus, that tells you what your accommodation is. Just try. See how close you can do. When you were 5 years old, you probably could have focused on your nose. you're losing your accommodation already. What happens is you lose the accommodation, and when you're 5, you can focus in on this. I used to wonder, why did anybody ever use a magnifying glass? Because if you want to see a bug, you just look at it, like you do in a moon with a telescope. As you lose your accommodation, you can't quite focus like that. So you focus here, and then here, and then here, and here. And then what happens at age 35? This is what's happening. So I'm going to read. When you're a little kid, you read like this. Okay? Bigger. And then you get a little bit older, and you read like this. Okay? A bit older, you look like this. This is fine. Here you are in your 20s. You're reading like this. That's about the closest you can focus. You get to 30, like this. 40, I can't read it anymore. My eyes are going bad. For the first time in my life, I never needed glasses my whole life. Now I need glasses. Ah! Actually, it's been happening gradually. You just never noticed it. So you get to age 35, you lose the accommodation. You go to your local drugstore for $10, $8. You buy a pair of magnifying glasses on frames. Now you can go to your ophthalmologist, and he'll charge you $150. Or you can go to your drugstore and buy a pair of these. And people say, oh, you don't want to go to the drugstore. You want to go see a doctor. Well, actually, I love these, $8 each. And you put them on. And now you can read. They're called reading glasses, okay? Because they give me that extra, people say extra magnification. No, they're not magnifying. What they're doing is allowing me to focus. They don't really, I mean, yes, I could use them as a magnifier. I could use them like this, but you put them on your eyes. And now, here's the odd thing. If I look at you, I don't want these. If I look up close, I want these. So I get these little, cute little half things that look like this, okay? Now I can read, and I can look at you. I can do both. Okay? And what is the downside of this? The downside of this is I'm showing my age. I look like an old man now. Why do I look like an old man? Because, in your experience, the only people you see walking around like this are old men. You don't, well, or old women, but they don't, they have tricks. I'll tell you the tricks. Okay. Now, there's another thing you can do. You can have regular glasses. Then you're just nearsighted. Hey, young kids are nearsighted. That's okay to wear that. Okay, but then you have to be able to look differently. So they have 2 different lenses, one on the top, one on the bottom. That's called a bifocal. So you get bifocals. And that's like this, but you can't tell as easily unless you look up close. And then everybody can tell you're old. And, some people don't want to look old. My feeling is older is better in every way. One of my favorite quotes from literature is, no wise man ever wished to be younger. I agree with that. I wouldn't go back 10 years under any circumstance. I wouldn't mind a little bit younger body, but if I had to give up everything I've learned, I would never do it. But here I am, looking old. Okay, you can get glasses that are bifocals, but they don't have a little line there. And these are very popular among people who don't want to look old. They're invisible bifocals. Okay, so those are extremely popular, particularly among women. But there's one other thing, and I want you to notice this. Those of you who are actors, you want to know how to make yourself look 10 years older all of a sudden? And you will start noticing this in the movies, but you'll also notice it in middle-aged people. And the fact, you notice these things without noticing you're noticing them. But the actor knows you'll notice them without noticing you're noticing them. And so the actor can fool you, and you won't know how you're being fooled. But let me give a little bit of acting. I will now suddenly I can look young and I can look old, okay? I can go over here and I can look young, okay? Okay, or I can look old. Now watch this. You will see this in the movies. You will see this among your more elderly friends. You ready? I'm going to... Okay? You ever see anybody do that? None of your friends do that. But get to someone who is over 35 years old and they have lost their accommodation, they're moving it into focus. Tips for the actors. We'll be do homework due tonight. Make sure you look at a white computer screen and you notice the colors.